Hello everyone, welcome to the next part of this lecture number 11. Again, in the previous part, we started with defining these proper and improper rational fractions. Then we saw that how to expand these proper rational fractions into partial fractions. And we did some of the examples when the Laplace transform function has distinct real roots. We also did another one with it had complex distinct roots as well. So today we are going to do a few more example problems where we are going to see the repeated roots, how to solve that. And then we are also going to see an example of what to do when we get an improper rational fraction. So let's get started from this part of the lecture. Okay, so here's another transform, Laplace transform of a function f of t, which became f of s. Okay, and eventually we are interested in to get f of t back. When we want to find the inverse Laplace transform of f of s, so we have to find eventually f of t. Okay, so if you look over here, I can already see that this is still a proper rational fraction because this is s1, and if I were to solve this, I'm going to get s4, right? So this is still a proper rational fraction. I can still expand it based on the things that I've learned in the past. Okay, sorry. So let's get started. So let's expand f of s, right? So if I'm going to expand f of s, I get 100 s plus 25 divided by s plus 5 cube. If you remember some of the rules that I've talked about in the 11b part of the lecture, the first slide, or the first or second slide, we talked about how to open up the repeated roots. And how to open up the repeated roots, the first over here is just s equals to 0, right? So I'm just going to define it as k1 over s plus. Now the repeated roots, you have to write down these as roots and in the kind of a decreasing order, or going from 3 all the way to 1 or from 1 all the way to 3. So for example, so k2, this can be expanded at s plus 5 whole cube, k3 s plus 5 square, k4 s plus 5 1. Okay, so this is how we can potentially expand it. Now, in order to solve this kind of a repeated root problem, there is an easy method to go about it, right? So what we are going to learn are kind of a new method actually in this part of the lecture. All three of the problems are unique. In order to solve this, what I'm going to do is I am going to create the denominators on the right hand side similar to the denominator on the left hand side. The denominator on the left hand side is s times s plus 5 whole cube. I'm going to create that denominator on the right hand side as well. So I'm going to multiply, for example, this term by s plus 5 whole cube, right? And divide that term as well. So in the denominator, I'm going to get s plus 5 whole cube. So I'm going to do exactly the same thing for all of these four to get the same denominator. So I can cancel s times s plus 5 whole cube, both from the left hand side and the right hand side. Okay. So this is what I'm planning to do. So begin by multiplying the numerator and the denominator of each term on the right hand side, such that on the denominator you're going to get this term. And then eventually we're going to cancel it out. And once we're going to cancel it out, we're going to open up the brackets. We're going to get the right hand side creating kind of a opening up the bracket and creating this kind of a polynomial with s cube, s squared, s1, s2, and then we're going to kind of equate each term. Okay, so before I get there, let's first do this thing, the method that I am talking about, right? So my left hand side should remain the same, 100 s plus 25 over s plus 5 whole cube. Again, I'm interested in creating again the same denominator on the right hand side for all the terms. In order to do that, I'm going to multiply k1 by s plus 5 whole cube over s times s plus 5 whole cube, right? So my denominator becomes the same for k1. k2, I just need to multiply with s, so I got the same term here. For the third term, right, which has s plus 5 square, I need, in order to get this, I need to in the denominator, I need to multiply it with s, and then another s plus 5, right, to make it s plus 5 whole cube. So I'm going to multiply it with s times s plus 5. And then finally k4, which is only s plus 5. So I have to multiply it with s plus 5 square. So denominator becomes s plus 5 cube, s plus 5 square. Okay, great. So this is what I ended up doing. The whole idea was to create the same denominators on the left-hand side and the right-hand side so that we can easily cancel them out. Now, what I'm going to do on the right-hand side is, since my denominators on the both sides will be cancelled out, I can just expand the whole right-hand side, right? So I need to expand all of these brackets, and then I can write the equation in the form of, with respect to x, all the different powers, right? So for example, my equations are going to come out to be, so for example, over here, let me actually, why don't I do this thing, right? So 100 times s plus 25 is 100s plus 2500. So this is left hand side, right? And then right hand side comes out to be k1 times s plus 5 whole cube plus k2s plus k3 s plus 5 plus k4 s plus 5 square, right? So what we need to do, we just need to open up all of these brackets and expand all of them and rewrite right hand side into individual powers of s. Okay, so k1 plus k4 comes out to be s cube plus 15 k1 if you were to solve this, plus k3 plus 10 times k4 comes out to be s square and then plus another plus 75 k1 plus k2 plus 5 k3 plus 25 k4 times s, and finally 125 k1. Okay, so this is the expansion, polynomial expansion of the right hand side of this equation. And again, left hand side of this equation is 100s plus 2500. Where did it come from? Over here. Again, expanding this side, right? Okay, so once we do that, the next thing that we have to do is we can equate the same coefficients and write the four simultaneous equations with respect to s, right? So for example, on the left hand side there is no s cube, but on the right hand side there is an s cube. So my first equation is going to come out to be k1 plus k4 equals 0. Second one, there is no s squared on the left hand side, but there is an s squared on the right hand side. So the next is 15 k1 plus k3 plus 10 k4 equals to 0 again. Okay, now the third one is this, and there is an s which is 100, and the coefficient of the s is 100. So I'm going to make right hand side is 75 k1 plus k2 plus 5 k3 plus 25 k4 equals 100. And after s, the only other one is a constant, 125 k1. 125 k1 equals 2500. Okay, so you got four consecutive equations, and you can solve all of these four consecutive equations to find all the 4k values, right? So for example, you can see that from this one you can find the value of the k1, right? And once you find the value of the k1, from this one you can find the value of the k4, right? Once you find the value of the k1 and the k4, you can put them into this equation and find the value of the k3, because k1 and k4 will be known. And once you know all of these values, then put them over here. So for example, this is your first step, this is your second step, this is your third step, and over here you're going to get the value of the k2 in the fourth step. So the final values after solving this is going to come out to be k120, k2 minus 400, k3 minus 100, and k4 is going to come out to be minus 20. Okay. Okay, so you got 4 simultaneous equations and you got these 4 values. Let's put them back in f of s and then find the inverse transform. Right, so I'm going to replace all of these values back over here and find the inverse transform. Okay. So my f of s is going to come out to be 20 over s, k1. K2 was minus 400. So minus 400 over s plus 5 cube. K3 minus 100 over s plus 5 whole square. What is it? Minus. Yeah, k4 is minus as well. And minus, k4 is minus 20 over s plus 5. Okay, awesome. So we got this expanded Laplace transform of the function f of s. What we want to do now is we have to find the inverse transform, right? And let me do it very quick. Inverse transform of 1 over s, you know by now we have done it so many times. Should be a unit step function. And then we have also done it for 1 over s plus a, e raised to power minus at times the unit step function. We have also seen this identity, right? So for example, Laplace transform of 1 over s square is t, right? So from here, if you have to find the Laplace transform of 1 over s plus a whole square, it comes out to be t e raised to power minus at u of t. And then finally, the Laplace inverse of 1 over s plus a whole cube comes out to be 2t squared over 2 e raised to power minus at u of t. Again, why? So for example, with the 2, a t gets multiplied. With the 3, essentially it's a power of t, right? So with the 4, it is going to come out to be, if in the denominator, you would have s plus a times s plus a to the power 4, right? So the t is going to come out to be n minus 1. Let me rewrite this, 1 over s plus a n, right? So this should be t raised to power n minus 1 over n minus 1 e raised to power minus at u of t. So this is how you can write kind of a genetic form of this inverse Laplace transform. Anyhow, once you find this is cool. I'm going to kind of replace everything back into the equation. I'm interested in, again, finding inverse Laplace of f of s. Should be f of t. So f of t is 20 over s. 20 times the unit step function minus 400 e raised with a cube minus 400 divided by 2 t square e raised to power minus 5t. Unit step function minus 100 e raised to power minus 5t times t. U of t, yeah, and finally minus 20 e raised to power minus 5t u of t. So you can take u of t common, and you are going to get 20 minus 200 t square e raised to power minus 5t minus 100 e raised to power minus 5t minus 20 e raised to power minus 5t times u of t. Okay, so here is your function back in the time domain, right? So in this example problem, we learned what to do when we have repeated real roots. So you kind of expand it like this, and then you make the left hand side denominators equals to the right hand side denominator. So you will get and then expand the polynomials to get multiple simultaneous equations, solve them to find all the constants, and then take inverse Laplace transforms to find the time domain function. So easy peasy. That was a simple example. Now I am interested in doing another very good example. But before we do that, right? So this is you can also kind of use some of these pairs. Potentially could be a part of your formula sheet, right? And we kind of ended up doing this distinct complex roots in the previous example, where we at the end of the day we ended up finding a function like this, but I did this whole spend another like 10-15 minutes in doing this derivation on how to get this thing, where we use different identities and to get to the bottom of this. Okay, anyhow, if you have distinct real roots k over s plus a, right, the inverse Laplace transform of this thing, right, so inverse Laplace transform of f of s becomes f of t. So e to the power minus a du of t. K over s plus a whole square multiplied with a t. When you get distinct roots, we get this. When we get repeated complex roots, we're going to get this. So I'm going to do an example of our repeated complex roots, and we're going to talk about how to solve this. And then I'm going to take advantage of this kind of an identity to get here rather than solving for the whole thing. Okay. So let's see the next example where we have repeated complex roots. If you look at the denominator, right, this is one of the previous examples that we did. If you were to solve the roots of this polynomial denominator, so right, so finding roots. So roots of denominator. Roots of the denominator is going to come out to be s12 is minus 3 plus minus 4j. Okay, so we have done this in the past. So now let's kind of expand this entire thing, right? So for example, you can also write f of s now as 768 divided by minus 3 plus s plus 3 s plus 3 minus 4j, s plus 3 minus 4j square, and s plus 3 plus 4j square, right? Okay, so here is your f of s expression in form of the roots. S plus 3 minus 4j square and s plus 3 plus 4j square. And again, we have repeated roots. If we have repeated roots, we already saw what to do with the repeated roots in the previous problem, right? Okay, so I'm gonna kind of solve this thing now and expand this thing, right? So f of s is this, let me read it, 768 divided by s plus 3 minus 4j whole square, s plus 3 plus 4j whole square. Okay, I'm going to expand this. First, again, in the repeated roots, right, so we can write one of the root with a square, one of the root over here with a square, another one with a less power, like 2 minus 1 power. Okay, so I'm going to do k1 over s plus 3 minus 4j whole square. Okay, and now I'm going to do another k2 s plus 3 minus 4j, right? So we got, this is how we treat the repeated roots. Then I'm going to do k1 prime, which is a complex conjugate of this root, s plus 3 plus 4j whole square. And the other constant is going to be the constant, again, k2 prime as well, s plus 3 plus 4j. Okay, so awesome. So I got kind of this this expansion of this proper rational fractions into partial fractions. And by looks of it, right, I only need to solve for k1 and k2, and then get k1 prime and k2 prime just by the conjugate's nature of it. Okay, in order to solve that, I'm gonna talk about one of the past ways of solving it, and then in addition we're going to need some new way as well. So the past way is I can find k1. Let's find with k1 to do what we have been doing in the past. In order to find k1, I can multiply everything. Multiply both sides by s plus 3 minus 4j whole square and evaluate at s equals minus 3 plus 4j. If you're going to do this, right, if you're going to multiply, for example, the right-hand side by s plus 3 minus 4j and evaluate by this thing, you're going to realize that the k2 will become 0, k1 prime and k2 prime, everything will become 0, and you're only going to be left on the right-hand side by k1. And the left-hand side, since you're multiplying by s plus 3 minus 4j square, so this term will be gone, and you are only left with the other conjugate part of it. So for example, you will only be left with 768 divided by s plus 3 plus 4j whole square, and I need to evaluate this at minus 3 plus 4j. Okay, so if you're going to put this thing, 768, s is going to come out to be minus 3, so minus 3 plus 3 will be cancelled out, 4j plus 4j, 8j, 8j square, right? So j 8 square, 8 times 2 is 8 power, 8 times 8 is 64, and j square is minus 1, right? 768 divided by minus 64, so the value of the k1 is going to come out to be minus 12. K1 is going to come out to be minus 12. Okay, great. So let's talk about the problem now. And why do we need a new technique? Now, can I find, so if I find k1, I know that my k2 prime, my k1 prime is a conjugate of this. So what should be the value? The value should be exactly same, because k1 is not a complex number. So k1 and k1 prime should come out to be exactly the same. Okay, and because k1 only has a real value and not an imaginary component, I want to find k2. The problem with finding k2 is, so for example, if I wanna, let's say, finding this k2, the problem is that if I will multiply everything by s plus 3 minus 4j, right, and if I'm looking at the right hand side, and if I multiply everything by s plus 3 minus 4j, I can see that I will be left over with k2, and in terms of the k1, I'm going to be left over with a denominator term, s plus 3 minus 4j, without a square. And then once I'm going to evaluate that at s equals minus 3 plus 4j, this is going to make k1 over 0 and infinite. So that is why I cannot just multiply it by the same way. So for example, if we multiply both sides by s plus 3 minus 4j to find k2, right, multiply and evaluate, and evaluate at s equals minus 3 plus 4j, right, right hand side is gonna look like at least k1 over 0 plus k2 plus other things, but we're gonna get this 0 thing, and that is why we cannot use exactly the same way to do it. So we have to find a solution, and the solution to this problem is going to be something very interesting. So in order to find the k2, we're going to do interesting thing. So the first thing is that, again, we will again multiply both sides by the same thing, s plus 3 minus 4j, that we did to find k1 square, right? And then we will evaluate at s equals minus 3 plus 4j. No, actually, before evaluating, we are going to do another interesting thing. Once we're going to multiply both sides by s plus 3 minus 4j, why don't I write this thing down? Okay, so just imagine on the left-hand side, you will get 768 divided by s plus 3 plus 4j whole square, because this term was cancelled. And then on the right hand side you're gonna be left with k1, right? And then then you're gonna be left with k2 times k2 times s plus 3 minus 4j whole 4j. And then of course there was one term in the denominator, so that will be cancelled, plus let's say k1 prime s plus 3 minus 4j whole square over s plus 3 minus 4 plus 4j square, and then you're going to have a k2 prime over here as well, and s plus 3 plus 4j, s plus 3 minus 4j whole square. Okay, so what we need to do is we are going to do two interesting things. One, we have to evaluate this at s plus 3, s equals minus 3 plus 4j. Okay, but before evaluating it, we have to take a derivative with respect to ds. So what is going to happen? So this thing, once we're going to evaluate this at s equals to minus 3 plus 4j, both of these terms will become 0 anyways, right? So I'm more going to be interested in both of these terms. Okay. Another thing that I need to do is I need to take derivative with respect to ds. So if I'm going to take a derivative d over ds, 768 over s plus 3 plus 4j whole square, sorry, and this is s equals minus 3 plus 4j, minus 3 plus 4j. If I'm going to take a derivative with respect to ds, k1 plus k2 s plus 3 minus 4j, right, I am going to be left over with, on the right hand side, the derivative of the constant k1 is going to be 0, derivative of k2 times 3 is going to be 0, k2 times minus 4j is going to be 0, k2 times 3 is going to be k2. The only term that I'm going to be left with on the right hand side is k2. So this is how you practically get actually k2. You multiply everything by the same thing that you have done in the past, by the square term, and then take the first derivative. And once you're going to take the first derivative of with respect to x, right, so this k1 that was a leftover is going to be out because it's a constant, and you are only going to be left with k2. So you can find the value of the k2 by taking the first derivative with respect to x of the left hand side, because on the right hand side only k2 is left. Actually, you can find with respect to s, you can find these derivatives as well, but eventually once you're going to evaluate everything at minus 3 plus 4j, these terms will be cancelled out. So I'm going to do this thing, so where my k2 equals d over ds, 768 over s plus 3 plus 4j whole square, right? So let me first solve this thing. 768 over s plus 3 plus 4j cube, right? And the derivative of the inside thing, which should come out to be, since the power 2, right? So minus 2, so it should come out to be minus 2 over here, right? And then now we can evaluate it. S equals to minus 3 plus 4j. Okay, so let's evaluate this as minus 3 plus 4j. So this should come out to be minus 2 times 768 over s minus 3 plus 3 will be cancelled out, 4j plus 4j 8 j whole cube, right? If you're going to solve this thing, you're going to get minus 3j, and again you can represent minus 3j by 3 with an angle minus 90 degrees. So the value of the k2 is going to come out to be 3 an angle minus 90 degrees. So the value of the k2 prime is going to come out to be plus 3j, or 3 with a positive angle of a 90 degree. Okay, so once you find all of these things, we can easily express f of s by, in the form of its partial fractions, minus 12 over, right, so k1 and k2 K1 and K1 prime was minus 12, and K2 and K2 primes were these complex numbers. So minus 12 over S plus 3 minus 4j whole square plus minus 12 over S plus 3 plus 4j whole square. It's K1, K2, no, sorry, K1 prime. Now K2 is 3 angle 90, 3 angle minus 90, or you can call minus 3j over S plus 3 minus 4j and plus 3 angle 90 degrees over S plus 3 plus 4j. Okay, sounds good, right? So this is how you can find the value of the f of s, again by expanding the partial fractions. And then I'm interested in finding the inverse Laplace of this to find f of t. I'm not going to do this exercise because we have done this kind of very detailed exercise 15 to 20 minutes in the previous example. I am going to find the function, write the functions as is, right? So over here, the final function after taking an inverse transform, and so of course apply all of these transforms and also take advantage of this table that we talked about with repeated complex roots, so that your final answer is going to look like something like minus 24 times t e raised to power minus 3t cos of 4t plus 6 e raised to power minus 3t cos of 4t minus 90 degrees. And of course, this is with a unit step function. So this is your final time domain frequency function f of t. Okay, so this is good. Now we are to the last problem of today's lecture. Okay. I should have probably had this in some sort of an animation. Okay, so in this final problem, we are going to look at the improper rational fraction and how to solve that. So here's your function, and it comes out to be an improper rational fraction. Again, most of the circuits does not come out to be improper rational fraction, so you don't need to worry about that for the circuits. But having said that, it's a good idea to understand how to solve for improper rational fractions. Since your numerator power is 4 and denominator, maximum denominator is 2, right? So again, so this makes it an improper rational fraction. And how to solve for improper rational fraction? Practically, you'd go through this long division process, long division that you have studied in, I don't know, in like 3rd, 4th grade. You're going to go through this process of the long division and then rewrite the improper rational fraction as a constant plus a proper rational fraction, right? So let's kind of do this interesting things. So what I'm going to do now is I'm going to do this kind of a long division here. Okay, interesting. Okay, so we have, I'm going to divide the numerator by the denominator. S4 plus 13s cube plus 66s square plus 200s plus 300. I'm going to divide this by s square plus 9s plus 20. Okay, so while doing this long division, let's first kick out the first term, which is s4. In order to kick out the first term, let me take the quotient as s square. If I'm going to, now I have to multiply these two things, right? If you remember how to do the long division. So you're going to get s squared, s4 plus 9 times s cube plus 20s squared. And then you're going to subtract this. S4 will be cancelled out. You will be left with 13 minus 9, 4s cube plus 66 minus 20, right? So you have to like subtract everything, minus. So once you're going to do that, 66 minus 20, 46x squared plus 200s plus 300. Nice? Okay. Now let me do it again. I get 4s cube and I have s squared. So if I will multiply this by 4s, I will get a 4s cube. 4s cube plus 9 times 4, 36x squared plus 20 times 4s, 80s. So I got this another term. Yeah, I should have started with, well, slightly on the left hand side. Okay, so I got, again, I have to subtract both of these, so I'm going to get a 0. 46 minus 36 is 10s squared. 20 minus 80 is 200 minus 80 is 120s plus 300. Okay, nice. Now I have 10s squared and s squared, so all I need to do is to multiply by 10. So I will get 10s squared plus 90s, 9 times 10, 90s plus 200. So 10s squared will be cancelled out, 120 minus 90, 30s plus 100. Nice. Okay. So, and I know that by doing a long division, I can rewrite this expression by quotient plus remainder, right? So this is your quotient. This is your remainder, if you remember, and this is your divisor. And we can rewrite this whole thing as quotient plus remainder divided by divisor. Beautiful. Okay. So this is exactly what we're gonna do now. We're gonna write this as is. So I'm gonna re-express f of s function by the quotient, which comes out to be s squared plus 4s plus 10, s squared plus 4s plus 10 plus remainder 30s plus 100 divided by divisor s squared plus 9s plus 20. Right, so this is beautiful. Now I can see that I have these individual terms, which I can easily find the Laplace transform of, inverse Laplace transform of, and then I got this term, and this bracket term is this bracket is a proper rational fraction that I can solve with the techniques that I have learned in the past. So let me start by doing this thing. 30s plus 100 divided by s squared plus 9s plus 20 can be, again, on the denominator, you have a quadratic equation, so you can find it, the roots. 30s plus 100 divided by s plus 4, s plus 5. You can further expand this into a over s plus 4 plus b over s plus 5. Now, I'm not going to do this thing, but you have done this like so many times by now, right? So in order to find a, multiply both sides by s plus 4, evaluate at s equals minus 4. In order to find b, multiply both sides by s plus 5, evaluate as s equals minus 5. So once you're going to do that, your a is going to come out to be, the value of the a is going to come out to be minus 20, and the value of the b is going to come out to be 50. So you can rewrite f of s. Not f, yeah, potentially I can rewrite the whole f of s. Or let me rewrite this. Let me call this as g of s. Let me rewrite g of s, that bracket term, as minus 20 over s plus 4 plus 50 over s plus 5. Now I'm going to rewrite as f of s with the whole thing. Okay. So my final f of s was, again, s squared plus 4s plus 10. These are the first three, these terms. And then a plus b, this g of s. Right? Let me just write g of s. So s squared plus 4s plus 10 minus 20 over s plus 4 plus 50 over s plus 5. Okay, nice. So once I do that, I already know some of the identities. So I know that Laplace inverse of, right, 1 over s plus a is e raised to power minus 80 u of t. We have used this in, like, I don't know, huge number of times. Similarly, I also know that Laplace inverse of 1 is your impulse function, because the Laplace transform of the impulse function of unit impulse is 1, right? Similarly, I also know that the Laplace inverse of a derivative of a function with respect to t. Sorry, this is not Laplace inverse, this is a Laplace. Laplace of a derivative of a function is s of f of s minus f of 0 negative. Since my initial conditions in our case is 0, we can simply write the inverse Laplace of s of f of s, right? S times some function should comes out to be the derivative of the function. Okay. All right, so let's do this thing. Laplace inverse of starting with minus 20 over s plus 4 should be minus 20 e raised to power minus 40 times ut. Laplace inverse of 50 over s plus 5 should be 50 e raised to power minus 5t ut. Laplace inverse of 10 should be using this, right? 10 times the impulse function, unit impulse function. Laplace inverse of 4 times s is, right? 4 is a constant with an s, and we know that it is s times f of s or f of t, so it can be an impulse function, the constant, right? So I can write it as 4 times, and since this is 4 of s, right, 4 times the derivative of the impulse function. And similarly, Laplace inverse of s squared can be the double derivative of an impulse function. Okay, so I'm going to replace all of this back in that equation, and my beautiful time domain equation is going to kind of come out to be the double derivative of an impulse function, dt squared, plus 4 times the derivative of an impulse function, plus 10 times the impulse function, minus 20 times e raised to power minus 4t. I'm going to take minus common so I can take out the step function, minus 20 and then minus 50 e raised to power minus 5t, and I took out a unit impulse function. So this is your time domain expression of f of s. Okay, so with that, practically this is the end of this lecture and a lot of topics of our partial fractions. Again, in this entire 3-part lecture, we started with that our circuits, integral differential equations can be converted into this function f of s Laplace transformed. And once we do that, they come in a kind of a polynomial denominator and the numerator way. And most of the case, they comes out to be rational fractions, proper rational fractions. And then we can convert this proper rational fractions, expand them into some of the partial fractions, and we learn different ways of expanding them. First, we expand into some of the partial fractions, then we solve those constants, and once we solve those constants, we can then find a simplified version of the Laplace transform f of s and then find the inverse transform. We looked at many different ways, right? When we have repeated real roots, when we have repeated conjugate complex roots, when we have complex roots, when we have real distinct roots, repeated real distinct roots. And finally, we also did an example where we have an improper rational fraction. So the whole idea is that this partial fraction analysis is applicable to proper rational fraction. So what you have to do is convert the improper rational fraction into a proper rational fraction first, and then solve the entire thing. So with this, I hope that you guys learned a lot. This entire lecture was, in summary, to simplify your Laplace transformed equations using partial fractions, and then take an inverse transform to find the time domain expressions. Okay, sounds good. We have to learn a couple of just interesting topics in the next lecture, number 12. And then we are going to do a lot more circuits in the Laplace transform. We are going to model our resistor, inductor, and capacitors in Laplace transforms, and our sources in Laplace transforms. So we're going to do more in the next chapter 13 as well. This lecture went a little bit overboard than our lecture time. So what I'm going to do is I'm going to make the next lecture slightly shorter in time. I think the previous lecture was slightly shorter in time too, I guess. Okay, sounds good. With that, thank you so much. Have a great rest of the day. Thank you. Bye bye.